what it does say on, well, I was going to say plan book, but it is up on the board. It says due tomorrow. Okay, so should you have that done, except for the last one, the last one's all you have left, you got a pretty good start on it. Okay, so with that, how many of you feel that I am still struggling with this?
Depends on if it's the last question.
Not the last question.
These are all balanced already, right?
Yeah.
Right, right. Okay, now you got to be careful. They're completed. That's two different concepts. Okay, so I just want to do a little bit of content here. Okay. I sure hope I never drop this on anybody's head. Well, it would, because this is maybe maple or ash. Okay? Because I don't think this is pine. Because if this was pine, you'd probably be able to bend this a little more. But this is some good quality maple or ash lumber. Okay. Later. And one observation I've made on that already, okay? From going forward, a good suggestion that I have for you. When you are working on these, okay, for writing, what is a good idea, or what's a good use of a writing utensil? Why pencils? Okay, and am I correct upon looking at that paper and saw all blue ink on there? Is that correct?
Yeah.
Okay, so when you're doing that in ink, you're going to say that it's nice and neat, and it's not that there's any mistakes on there, but it's human nature. When people make mistakes on these things, this is what people tend to do. Okay? Maybe they're writing a term out and the numbers are supposed to be 1, 2, 2, 1. Oh, that's not right. So then we do this. Don't do that. Okay? If you have this and you know that it is wrong, that has the exact same effect. Okay? Just put a line through it. You don't need to scratch it out like that. If you want to make people like myself upset, do this. Keep doing that.
My bad.
Okay?
Who does that? That is
Okay.
so immature.
So, yes, that infuriates me because it's not neat, it's messy, and it makes it hard to read.
So do you write them in the line? Write your answer.
No, just put it, maybe if it's not 1, 2, 2, 1, maybe it's supposed to be 1, 2, 1, 1. Something like that. You don't need to scratch out the whole thing. That's my point. And then even if you are writing these out, which you will be responsible for finishing equations, and you have something like this, but no, it's supposed to be lithium carbonate, okay? Well, just do that. You don't need to scratch out the whole thing, and it sounds like someone's scratching right now with their pen.
Oh my.
Okay? I mean, I don't have the best of hearing, but something like that just stands out. Okay. Because chances are you're going to make mistakes on here, and when that happens, if you do it in pencil, it's much, much easier to correct them. And I think you would agree with myself in that nature. Okay. So, so this is where we left off with, correct?
Yeah.
And we finished this equation, correct?
Yeah.
And we balanced that equation, correct?
Yeah.
Okay? So when you are writing a chemical equation or a chemical reaction, this is what you're doing and why you are doing it, okay? Because what it does is it's a very useful tool, and we will do that together as a class, perhaps sometime, maybe next week at the very earliest. We will use a chemical equation or chemical reaction, and you will be making predictions. So you can mathematically predict how much of a product you should make. Okay? Not how much you actually make, but how much you should make. Because when you boil that down, really it's just a percentage. Okay? So with my point with this is whether it's volleyball and you are serving and you get the opportunity to serve 10 times, how many times should it be in? Ideally 10, but realistically, how many times do you put the ball?
9.
Okay, maybe 9 is probably fairly realistic, but I would go with probably 7 or 8. Okay, until you maybe your way all the way to the varsity level, where it's probably expected that serving percentage goes from 70% to maybe 85 or something to that nature.
I thought we were talking about varsity.
No. Okay. So then at any level then in basketball, as a team, your free throw percentage, if you shoot 30 a night or 30 on a given night, how many of those 30 ideally would you like to make? All 30 of them. But realistically, how many out of 30 is the team going to make?
20.
Maybe it's 25, but I think that's probably a little high. I would say probably somewhere around 22, 23, somewhere in that nature. Okay? Realistic. Not everyone shoots free throws the same way. Some people are better at it than others. So how do you get better at it? Well, sometimes it's practice. Okay? Need to get a leg up on things. Mm-hmm.
Good job.
Yeah. In case you're wondering, I'm carrying a leg. That's what we mean by get a leg up on things. Oh.
Anissa.
I got it. Look at the toes.
Okay. So, undo that one, that one. Okay, we're getting close. Okay. All right. So coefficients are the really big numbers. At the beginning of this presentation, it's where you saw 1, 2, 2, 1. Those are coefficients, or 1, 2, 1, 1. After we said don't scratch them out like with I've noticed before with a pen, just put a line through it. But ideally, use a pencil. Okay. And I think we've talked about this before when it boiled down to Buzz Aldrin and Neil Armstrong, and of course there were, I think, Jim Lovell maybe. I don't know how accurate that is, okay? And you don't hear that third name very often because it just came down to who was closer to the door, I think, when the astronauts landed on the moon back in July of 1969 to walk on the moon, okay? But in that sense, I think what we have talked about before, why would someone want to go to the moon? Knowing that you might not return.
For the money.
No. For the
I don't think it's. I think probably more so for the notoriety
The discovery.
and the being infamous with that, because obviously we still talk about these individuals, Buzz Aldrin and Neil Armstrong. Okay, and I believe was it Neil Armstrong that was the first one to walk on the moon?
He was the first one that touched it. It was supposed to be Buzz, but his door got stuck.
Oh, yeah.
Oh, okay. And I don't know how accurate that is. It was my interpretation that Neil was the first one because he was closer to the door. I don't know. You could be right too. But regardless, sometimes it's one of those phrases that's infamous throughout history. When we saw that video about hunting the elements, okay? Blimps back in World War I used hydrogen gas. But what might be a problem with any gas off of that periodic table? They're highly flammable, okay? And what had happened is when I'm not sure which blimp it was that was set to land in New Jersey after coming across the Atlantic Ocean. It's one of them infamous phrases that, of course, there was radio coverage at that time. But where were the TVs at?
Not around.
Yeah, it was in the 1920s. So TVs were not, or TV was not invented yet. So over the radio, depicting what you're actually seeing is a large fireball. And what does one of the radio announcers say? Oh, the humanity with this. Because, oh my gosh, what's going to happen to all these people in this fireball that's starting to burn right in front of people? That is one phrase that lives throughout history. Another one is one you could say back to the moon landing, the Apollo mission number 11. Okay? When Neil was walking on the moon, there is a misconception about the accuracy of what was actually said. Because what he actually said was, this is one small leap for a man and one large step for mankind. But that's not what we hear. Does anyone know what you actually hear?
Bunch of rat.
One small step for man, not a man. One small step for man, one large step for mankind. Now,
Giant leap.
is that what it was? Okay. So with that, again, that going back to that central question, maybe it's the notoriety of wanting to go to the moon. That was a chemical reaction, I think we talked about this, that was utilized for starting the booster rockets to get back off of the moon. Should that not worked correctly, you would be stuck on the moon until you could get another landing on there. And back in 1969, that would not be very common. That would probably be your demise, is not surviving on the moon. Not because these individuals probably weren't healthy, they probably were, but there's only so much oxygen. There's only so much time that you'd be able to stay on the moon inside this, I don't want to say shuttle, but capsule. That's the right word I'm looking for. Okay. So just think if you were one of the NASA engineers that was responsible for doing these calculations. You have to have the right amount of substance, apply it at the right time in order for these booster rockets to take place and get them back off of the moon. So there is practical uses for these chemical reactions. Okay, so I said I want to do that one, and then we'll stop at the end of this. So when you look at this, when iron is exposed to air and moisture, it corrodes or rusts, forming iron 3 oxide. So what can you presume or tell me everything you know when you see iron 3 oxide if you have to write that out in a chemical equation or reaction? Iron has a charge of +3. What does the oxide ion have for a charge?
-2.
Okay, so keep that in mind. We will address that here in just a moment. Now, one of the things that I can't answer either, that bottom statement, this leads to more oxidation and destruction of the structure. For anyone who owns a pickup truck, where is the most common place that that is a problem? At least I think so.
Cab corners.
I don't think so, not cab corners. Can you be a little more specific when you say over the tires? These, okay, maybe we're using terminology you don't understand. To me, those are called wheel wells, okay? So is it the front wheel well? I almost said real well, okay? Front wheel well or back wheel well? The back one, okay? I don't know why that is. I suppose just because, okay? I don't know if there's more room for that water to get up underneath your chassis around your engine block so it doesn't rust around your front wheel wells as often, but your back wheel wells are so susceptible. If you said wheel wells fast 3 times, I don't think I could do it.
Wheel well.
Okay, I guess I struggle with that. Okay. But I think if you're using other terms along wheel wells, it makes it a little more difficult. Does everyone have this content that wants it?
Yeah.
Okay.
Is this the vocab?
That is. It's on page 2, correct? Okay, so vocabulary has not formally been assigned, but next week it probably will be, and that will be uploaded to Plan Book. Perhaps be looking out for that next week. Because, now be honest, how many of you actually have ever gone to a teacher's Plan Book site?
I've been there.
Well, actually,
How many have you looked at the Science Plan Book site?
It says
Just
you
don't
have to
lie
log
on
you have to
it.
log
Just
in,
don't
and
lie.
I've tried like 5 different passwords.
only gets
Oh.
YouTube channel.
You just click on the picture.
Hey, you don't go to Plan Book. You
I
go
saved it as
on-
his bookmark, like Mr. Rickman's book a year ago.
Oh, okay. Well, that's above and beyond my knowledge. Okay. So, when we look at this, what is steel? Not S-T-E-A-L, where you take something. That's why I have you hand the papers to me. Okay? But S-T-E-E-L is a type of metal. So what is the major composition of steel? Okay? The reason we ask that is iron a tough substance?
Probably.
No, not really. It's
Is it iron?
a fairly soft metal, although you do not take just plain iron out of the ground. You don't take just plain aluminum out of the ground. Same thing with copper, nickel, any one of those metals. You just don't take the raw metal out. It's in an ore, which is O-R-E, not O-R, but O-R-E, okay? But regardless, if we're talking about steel, okay, the major component is iron, okay? Well, what happens if you add this to it? It's in the atmosphere,
Oxygen.
okay? And then what happens is it's not just oxygen, but it's the water vapor in the air, which has oxygen in it, okay? Is there something significant we need with this oxygen, though?
Hydrogen.
No.
Tin.
2. Oh.
Why does A2 have to go here?
It's because, yeah.
Okay, it's just human nature. People are going to forget this. It's a mistake. We want you to learn from those mistakes. Then we see that iron 3 oxide is going to be produced. We'll see this. Why would we see that?
I have no idea. Because you need 3 oxygen.
No.
You need 3 iron.
Because what did it say in your handout when we say iron 3 oxide? Roman numeral what? Roman numeral 3. But what does that 3 mean? A subscript of 3 or a superscript or charge of 3? Okay, it means the charge, not the number. Again, human nature. We will see this. Okay? It happens with juniors. Okay? We still have not learned from that mistake. Okay? Then does this 2 automatically come over here?
But it's not
It doesn't because they don't.
But what is iron 3 oxide, though? Okay, we've got our iron 3, but what's the charge of oxygen?
-2.
Okay, so what's the least common multiple between those? So how many oxygens do you need then?
3.
You need 3, not 2.
And you need 2 iron.
Right, okay? So if we wanted to balance this now, what do we got to do?
Yeah.
Okay, are we getting a little more comfortable with balancing?
Yes.
A little bit.
Okay, because remember, we got 3 lines because there's 1 here, 1 here, and 1 here. So again, these are all 1s right now. But we want to balance this out, okay? So what are some elements that we see?
Iron.
Iron and, so iron's left,
1.
iron's right,
2.
oxygen's left,
2.
oxygen's right.
3.
Okay? So, we need, these come in pairs. This is an odd number. We got to get that to an even number. And how do we do that?
Times it by.
Do what?
Times it by 2.
Okay? So, once we do that, that gets distributed to the entire compound. How many irons is this?
2.
How many irons is this?
4.
So, these are our coefficients. How many oxygens do we have now?
6.
Okay? So, what do we got to do to the left-hand side
Times
now?
iron by 2.
Okay? Do that. That's a pretty simple fix. 2 times 1.
Oh wait, times it by. What? Times it by 4.
You said 2.
Yeah, I meant 4. Times it by
Okay.
4. Oops. And then times oxygen by 3.
Okay? So now, this was a 1. What is it now? 4. This was a 1. What is it now? This was a 1. What is it now? Okay. Okay? All right. So I want to show a couple of examples really quick because I think just the practice of the balancing will only help you out. Okay? Because sometimes what gets to be confusing, here again, it's going to be human nature that's going to lead you to this. Okay? So, hydrochloric acid, okay, has a formula of HCl, the same type of acid you'd have in your stomach that is going to be secreted in your stomach so it can act with another inactive enzyme to digest your pulled pork. A lot of biochemistry and physiology involved with that. So the same substance is found in your stomach. But in this case, okay, give me an example of, give me a metal.
Iron.
Okay, Copper is what I heard first.
Zinc.
Okay, so
Hydrogen.
is this cupric or cuprous? What I mean by that is it +1 or is it +2?
+2.
Okay,
Plus, wait, what?
so therefore we're telling you that this is going to be a +2 charge. Okay, the reason that that is significant is because this single replacement reaction, when we start classifying these, you need to know how to finish these.
Do we have to do this, like all this stuff on any of these on this sheet?
No,
Okay.
all the equations are finished on there.
I didn't think so.
So this copper boots this hydrogen out, so now you've got copper chloride. Okay? And then just plain hydrogen. But this side is not done yet. Okay?
Why does copper and chloride go together?
Because this breaks that molecule apart right there.
So hydrogen has to be a +1.
Because they both have positive charges.
But doesn't hydrogen have -1?
And a
Now if it has 1 electron to give away, it's only if you're dealing with organic compounds that hydrogen have a -1 charge. But we're not talking about organic compounds.
How do you, like, if you give us a word sheet and we have to figure it out, how do we figure out if hydrogen is positive or negative?
It's always going to be positive.
Is it
Always positive. Just say always positive.
always positive?
There you go. It's
All right.
always positive. Yes.
Okay, so the problem. So hydrogen will have to be a +1, right? And so
Right.
since Cu is +2.
So we know that this is right because we said start with their negative ions. What's the chloride ion?
-1
What's the charge of hydrogen?
+1.
So does that add up to 0?
Yeah.
That's why there's nothing changed here.
So the Cl on the other side would have to be. There'd have to be 2 of them.
Okay? The charges don't change. This is still -1. Okay? What's the charge of that copper?
2.
That's why we said you need to pick what that is. Does that add up to 0?
No,
It does
has
not.
2 chloride.
You gotta have 2.
Yeah.
Okay?
Yes.
Is that it?
That'll work.
Do we believe that?
Yes.
Yes.
That is 100% wrong.
You still need to stabilize it.
Why is it wrong?
Because what type of substance is hydrogen?
Gas.
It's a gas.
No.
When you put that oxygen up there, is oxygen a gas?
Yes.
What did you have to put behind that?
2.
Why? 2 is right, but why? They're called what? Is one of your vocab terms too. We had it last chapter. Starts with a D. It's a diatomic molecule. So you have to have a 2 behind here. Okay? So, how many of you think this looks like it's difficult to balance?
I could do that by myself.
Okay? So, there's only one coefficient that you need to put up there.
Can I go up there and do it?
No, not when it's recording.
Okay.
You only have to put a 2 in front of hydrogen and chlorine.
That's right. There's only one coefficient you need because before we started, we had copper 1 to 1. We had hydrogen. We had 2 to 1. And we had chlorine 1 to 2. Okay? Does everyone agree with that so far?
Yes.
Yes.
Okay? So if we have 2 hydrogens on the right and only 1 on the left, you're going to change this 1 to a what?
2.
So upon doing that, how many hydrogens is that?
2.
How many chlorines is that?
2.
Okay? So if you had 4 blanks, this was a 1, you changed it to what?
2. 2. 1.
1.
2, 1, 1. Okay?
I like this.
Okay? So now, what we want to discuss then is something a little stronger like sulfuric acid. Sorry?
Oh, I already got that.
Okay?
So every single gas has 2 of them?
Except noble gases.
All right.
Okay? So something a little notorious or stronger, H2SO4. Okay. Battery acid, you can say we need another metal. Okay. So now, do we need to write the charge of aluminum down like what we did here?
Yes.
No,
No, never mind.
because copper has more than one charge. Does aluminum have more than one charge? No, it only has a charge of what?
Plus 3.
+3. Okay? Now, notice there was no subscript here or here, but two subscripts ended up over here. Why did that hydrogen have to go there?
It's by itself.
Because it's diatomic when it's by itself. Why did this 2 have to go here?
Because it'll stabilize copper and chlorine.
You had to do that because of the least common multiple. The charges have to add up to what?
0.
Right. So what is -1 times 2?
-2.
What is +2 times 1?
2, 1. 1.
+2 times 1. So +2 plus -2 equals what?
0.
+2 plus -2 equals
Is 0. Okay? Now, here you're utilizing what you learned last chapter. What is the charge of the sulfate ion? No. -2. Okay? What's the charge of hydrogen?
+1.
Okay? The charges will not change when they go to the other side. So sometimes, here you didn't see any subscripts, but they ended up over here to balance out the compounds. Okay? So if this follows the same path and splits right here, this aluminum boots that hydrogen out of there. Okay? But bonds to the sulfate ion on this side.
So it'll be A, L.
So do you think, will these subscripts go over there?
No.
It's a trick question.
Quite possibly, yes.
Yes and no.
Okay? This 4, that 4 is part of that formula. When you learned it last chapter, these subscripts, whether it's this one, whether it's this one, or whether it's this one, these subscripts, that's not PO3, it's supposed to be PO4, those will go to the other side of the equation always because it is part of the formula. Okay? So when we see that, if what bonds together? 2 positive charges together, 2 negative charges, or a positive and a negative charge? Okay? So what type of charge does aluminum form?
Positive.
Okay? So can that aluminum bond to this hydrogen?
No.
No, it cannot. But can aluminum bond to this sulfate?
Yes.
Yes, it can. So we write this as SO4. Again, why is that 4 there?
Because it's part of the.
It's part of the formula that has to go over there because it's attached to it. Okay? Then what do we have left over? Just like we did up there, H2. It's just a coincidence that that 2 goes over there because it was needed to balance out the compound, right?
Yes.
What is +1 times 2?
2.
Positive, I know what you mean. +2. How many sulfate ions is this? How many sulfate ions? One sulfate ion. Okay? So if it's one sulfate ion, just like you had one chloride ion, what is a -2 charge for one sulfate ion going to equal? Negative what?
2.
-2. Okay? So if this is -2 and that's +2, will that add up to 0?
Yeah.
Yes.
Yes.
Okay? So that means that once we get over here, if the charges don't change, which they don't, what's the charge of aluminum? Does that add up to 0? So what did you learn last chapter to write out what aluminum sulfate is?
The least common multiple.
What is the least common multiple?
6.
So what is 6 divided by 2? Okay, so we need 3 sulfate ions. How do we illustrate 3 sulfate ions? Just tell me. Put it in parentheses. And then what is 6 divided by 2?
2.
Or 6 divided by 3 is 2. Now you can go ahead and proceed to balance that. So should we just leave that up to you?
Yeah.
Okay.
Wait, can we do it and then once we figure? Oh, look, can we do it and then we do it later, like as a class?
Once they figure it out, can.
Sure. And then
Yeah.
on your paper, last thing, is there anything that you wanted to go over before we leave today?
Can we do the last question?
Yeah, last one, please.
I got it done, but I don't know if it's right.
I'm just, how many of you pay attention during class? How many of you know that we wrote this down up on the board? And we did this together already.
I wasn't here, but I
Okay. So how many of you were here?
probably would.
Okay. Did anyone write number 10 down on their paper?
We did number 4.
Okay. I thought that at some point we did this exact same problem.
No, we did number 4.
Not when we handed it out, but somewhere during these presentations. Okay? In a combustion reaction, you're always going to get CO2 plus H2O. Okay?
We did.
So that one, I'm just wondering, we have one person that we did do that. So you wrote it down. Huh. We go over something during class, we find value to write it down. Oh, what an amazing idea.
That is so smart. I should have done. I don't think I was here though. I didn't watch the science channel. I should have.
Okay, well, all right. So, a quick way of doing this, okay?
We do it.
So, how many carbons are on that side?
1.
How many carbons are over here?
3.
So how do you get this up to a 3?
Times it by
Multiply it by 3.
Okay? How many hydrogens is this?
8.
Okay, and how many hydrogens do you have over here?
2.
times it by 4.
Okay? So now look at your oxygens. What is 3 times 2?
6.
And then what is 4 times 1?
4.
So 4 plus 6 gives you what?
10.
So 10 oxygens over there and 2 over here means you need what?
5 by 5.
Yeah, I definitely did this wrong. I wrote a 12 there.
Okay? So that is number 10. You probably had it done already because we did it in class. Huh. What a novel idea, writing things down when we go over them. Yes?
I feel like
Number 3. I don't.
Number 3. Okay?
I mean, I can show you.
Number 3 is actually fairly easy. It's your simple math that is letting you down.
I don't know what have I done something wrong yet?
Well, for one, I see a lot of scratching on there. Why is that?
Because I kept looking at it.
What are you're doing this in pen. Why are we doing this in
I
pen?
did it yesterday. I don't know.
Okay? So, very quickly, you put a 4 there, that's right, because of the nitrates. What's 4 times 1?
no answers and stuff.
4.
Okay? How many nitrates do we have here? What's 1 times 4? So your nitrates are balanced. How many chlorides are here?
4.
So how many chlorides are there right now?
1.
So how do you get this up to a 4?
Put a 4 there. I got
Okay.
a 4 there.
I can't tell because it's all scratched out. Okay? So then you put a 4 here for that hydrogen, right?
Yep.
So it looks to me like you got it balanced now.
But I still got that.
Okay? What's 4 times 1 for hydrogens?
4.
What's 4 times 1 for that hydrogen?
4.
So now you got 4 hydrogens on each side.
Yeah. No, for NO3.
Okay. How many nitrate ions is that?
What? 3.
How many nitrate ions is that?
Where? Right there?
Yes.
1.
Right. But when you put a 4 there, what's 4 times 1?
12.
What's 4 times 1?
Oh, 4.
Okay. So then, how many, if I put my thumb over that, how many nitrate ions is that?
3.
How many nitrate ions is that? 1. But you have what on the outside?
4.
So you got 4 nitrates there. How many nitrates are here now when you put that 4 there?
4.
So they're balanced.
Okay.
All right. So this last one, I'm just going to write this up here really quickly. Looks to me like we got 3 sulfates over there. So we're just going to put a 3 here. Your sulfates are now balanced. We got 2 aluminums, and then we got 6 hydrogens on each side. Okay, we'll catch up to you next time. Your numbers were 3, 2, 1, 3.